Today is Saturday, 7th of June 2025, 6 a.m. Eastern Time. This science and technology update is brought to you by Preety Capital, your trusted source for intelligent insights.
Imagine healing happening inside your body. And I don't just mean, the usual way. I
Right.
mean guided, directed repair happening right down at the cellular level, but without needing a single cut. No surgery.
Uh-huh.
Picture tiny structures being built or damaged tissues getting mended, and it's all being guided by, well, sound waves. Seems like science fiction almost.
It really does.
That's the incredible promise of what we're diving into today.
Mm.
Deep tissue in vivo sound printing, or DISP for short.
Mm-hmm. DISP.
We've got a whole stack of sources here, research articles, updates from labs, you name it all, talking about this amazing emerging technology.
Yeah, quite a bit of material.
So our mission, really, in this deep dive is to unpack all of that, pull out the key bits of info, and figure out what this could actually mean for you.
And it really does feel like a significant leap looking through these papers, a leap forward in, well, biomedical engineering. It seems to break past some old limits on internal repair. Oh, yeah. The potential they outline in these sources is quite remarkable, almost hard to wrap your head around until you dig into the specifics they're detailing.
Maybe let's do that, diving right in.
Mm-hmm.
Based on these sources, how do they define DISP? What exactly is this technology doing?
Okay, so at its core, DISP is about using highly focused ultrasound waves. Think like really concentrated sound beams
Right.
to precisely manipulate biological tissues, but within a living organism. That's the key.
Inside the body.
Exactly. The sources keep emphasizing this in vivo part, the ability to reach deep inside non-invasively. They describe it as creating 3D structures or modifying existing tissues right there inside without any cuts.
So like 3D printing.
Sort of, yeah.
But the ink is your own body cells and maybe some biomaterials, and the printer head is sound.
That's a good way to put it. Yeah.
It's still pretty wild to picture.
Yeah.
How does sound, which, we usually think of for hearing, maybe sonograms, how does it actually build something? Or change tissue? What's the physics and biology going on here, according to the papers?
Well, what's really fascinating is the range of mechanisms they talk about. It's not just one thing.
Okay.
They explain that by focusing high-intensity ultrasound energy to a tiny, tiny spot deep inside tissue, you create these very localized effects.
Mm-hmm.
One key effect they highlight is controlled cavitation. That's basically making microscopic bubbles form and collapse very rapidly.
Bubbles inside you.
Yeah, but it's not random. They show how this precisely controlled bubbling creates these little mechanical forces, think tiny pushes and pulls.
Right.
And that can actually nudge cells around, break apart clumps of cells if needed for printing, and even make the cell walls temporarily more permeable, which helps get therapeutic agents or growth factors right to that specific spot.
So it's not just like heat or vibration. It's literally using the force of these tiny popping bubbles.
Exactly. That's a big part of it. But it's not the only mechanism.
Okay.
The sources also describe creating localized heat, again, very controlled when the sound waves get absorbed by the tissue.
Right, like ultrasound therapy sometimes uses heat.
Precisely, but much more focused here. And that thermal energy, along with other mechanical forces from the sound waves themselves, they often call it acoustic radiation force. Like the sound wave is physically pushing particles or cells.
Oh.
All of that prompts specific responses from the cells. They detail how these forces and the heat can trigger cells to start dividing, that's proliferation,
Mm-hmm.
or to specialize into the different cell types you need for repair differentiation,
Got it.
and even to lay down the scaffolding, the matrix of new tissue.
So that's the connection. The sound isn't just pushing stuff around. It's actually telling the cells what to do by creating these specific little microenvironments.
You got it. That's exactly the idea. And the sources spend a lot of time on the control aspect.
I bet.
They explain how by meticulously, really carefully controlling all the ultrasound parameters, the frequency, the intensity, how long the pulses are, the wave amplitude, researchers can achieve incredibly precise localization.
Pinpoint accuracy.
Exactly. And they can pattern these effects in 3D. It usually starts with a digital blueprint, like a CAD model, of the structure they want to build or repair.
Okay.
And that digital model gets translated into a complex sequence of ultrasonic pulses delivered from outside the body to guide the whole process internally.
This just feels like it unlocks completely new possibilities.
Mhm.
So what are the big applications? What are the sources most excited about? What could this actually do for people that's difficult now?
Well, if we look at the bigger picture, the sources really point to regenerative medicine as the primary area.
Makes sense.
And they go beyond just saying tissue repair. They talk about specific, really tough challenges like repairing deep, soft tissues, think muscles, tendons, ligaments, maybe from sports injuries or accidents where surgery is complicated or recovery takes forever.
Yeah, this can be tricky.
Definitely. And they also talk about hard tissues, like fixing defects in bone or cartilage, which are notoriously hard to heal well without using grafts. But what's particularly compelling, and it comes up in several reports, is the potential for repairing really delicate, complex tissues. Things like damaged heart valves,
Wow.
or maybe even neural tissue in the brain, potentially without needing to open the skull.
Repairing a heart valve with sound waves from outside, that really does sound like a leap.
It absolutely does.
And because it's all happening inside, the sources emphasize that this lets you incorporate living cells, right? That seems crucial.
Yes, that's highlighted again and again as a critical advantage. This in situ capability means they can deliver not just scaffolds or growth factors, but actual living cells directly into the site while it's being worked on.
Uh-huh.
And that's vital if you want to create tissue that's actually functional and alive, unlike, say, putting in a non-living implant.
Right.
This capability also ties directly into the personalized medicine angle. The sources suggest it could allow building repairs tailored exactly to your own anatomy, your tissue type, maybe even using your own cells harvested earlier.
Very personalized. And you mentioned drug delivery before. How does DISP play into that?
Yeah, it seems to have significant potential there too, basically leveraging that same pinpoint precision.
Okay.
The sources describe using the focused ultrasound to do a couple of things. Either it temporarily makes the cell membranes in a very specific area more permeable, letting drugs get inside more easily.
Opens the door a bit.
Exactly. Or it can even be used to create tiny microscopic channels within the tissue for a localized, sustained release of a drug right where it's needed.
Like a little depot.
Precisely. And this targeted approach, they explain, could potentially boost how well therapies work, especially for hard-to-reach spots like tumors deep inside organs.
Right.
And at the same time, it could drastically cut down on the systemic side effects you often get when a drug floods your whole body.
So it's not just about building new tissue, but maybe making current treatments much more effective and safer for specific problems.
Exactly. It's all about precision intervention. And that loops back to the non-invasive nature we talked about.
Yeah, that seems huge.
It's definitely one of the most crucial advantages they detail across pretty much all the sources. No cuts means minimal trauma, much shorter recovery times compared to surgery, and, a much lower risk of infection.
All big pluses.
For sure. And they make a strong case for ultrasound being safe. It's non-ionizing radiation, unlike X-rays or CT scans.
Point.
And critically, it can travel through skin and overlying tissues to reach deep layers without damaging them on the way. That's vital if you're talking about treating, say, an internal tumor.
It feels like this tech, amazing as it is, probably relies on other recent advancements too, right? What allows this kind of precision with sound? It can't just be the ultrasound transducer itself.
You're absolutely right. The sources definitely emphasize that. Recent progress in other fields is critical for making DISP work.
Like what?
High-resolution imaging is paramount. Things like sophisticated real-time ultrasound mapping are mentioned, and also integrating guidance from MRI or CT scans.
So you can see exactly where you're printing.
Exactly. That gives the visibility needed to guide the focused ultrasound energy to the right tiny spot with the accuracy required, and also the complex patterns and control needed. That's only possible because of sophisticated computer algorithms and advances in the transducer technology itself, the things that actually generate the sound waves, which can now shape and focus the sound much more precisely in 3D.
Okay, so it's a convergence of technologies. Yeah. It sounds incredibly powerful, very promising. But, there's always a but. When you're dealing with something this new, working inside a living body, what are the big challenges? What hurdles are researchers still facing, according to these sources?
Yeah, the sources are quite upfront about the fact that, significant hurdles remain before this is something you see in every hospital.
Okay.
A key challenge they discuss is needing even better imaging resolution to guide the process, especially when you're working in complex or moving environments, like inside organs that shift when you breathe.
Right, the body isn't static.
Not at all. So getting that sub-millimeter precision and verifying it in real time inside a dynamic system, That's still really difficult. They also highlight biological variability,
Yeah.
meaning different tissues just respond differently to the same ultrasound settings. What works perfectly for muscle might not work for cartilage. So, developing robust, standardized protocols that are tailored for the huge range of tissues in the body, that's a major ongoing research effort.
Lots of fine-tuning needed.
A massive amount. Fine-tuning all those parameters we mentioned, frequency, intensity, duration, to get the maximum therapeutic benefit while being absolutely sure you're minimizing any unwanted side effects or off-target impacts. That's still a huge focus.
So, okay, looking across this whole stack of sources, DISP really is presented as a potential game changer.
Mm-hmm.
I mean, from maybe replacing invasive surgery for complex repairs,
Right.
to totally changing how we deliver drugs, to literally engineering new tissue right where you need it, inside you.
It's definitely depicted as a foundational technology for the future of medicine. Something that could fundamentally shift the paradigm in fields like, bioprinting and regenerative medicine. It just offers a totally new way to interact with the body's internal environment for healing.
This deep dive, yeah, it's given us a really fascinating look into the potential power of sound waves when they're precisely controlled working inside the body.
It truly underscores how physics acoustics, really combined with advanced computing and imaging, can mesh with biology in ways that could just redefine healthcare possibilities.
So wrapping up, what does this all mean for you listening? Consider this. If sound waves, guided by digital blueprints, enabled by all this cutting-edge tech, can actually build and repair tissue inside your own body, how might that challenge our basic ideas of natural healing versus engineered guided repair in the future?
Mm-hmm.
What happens when healing becomes something you can specifically design, maybe even print on demand? Definitely something to think about as this research moves forward.